Hello, hello, and welcome to a fantastic interview here. We have Raza from the Scroll team here to talk to us about Scroll, about L2's, about ZK stuff. He's a good buddy of mine. We've been friends for some time. I'm excited to get into this candid conversation. Raza, how you doing, man?
Hey, Patrick. Well, thanks for having me. Doing great and super stoked to get this session going with you.
All right, badass. Me too. So, but we were talking a little bit backstage before we started this up. We were going to jump into a couple questions, but Raza actually came prepared. You have a little slide deck for us, yeah?
Yes, sir.
All right,
I'm
let's do it.
gonna. Awesome. I'm just gonna go ahead and share my screen. Present, share screen.
Boom, we got it.
Slideshow mode. Let's go. Yeah. So before we go deep into the conversation, want to give everyone sort of context. Make sure we explain a little bit about what we're going to talk about today, and then we can go deeper. And I will let Patrick grill me. But yeah, I'll get started. Zero knowledge and scaling Ethereum, talking about Scroll.
We're gonna
A
put
little bit.
you. We're gonna put you under the gun. We're gonna have you do some share screen, show some code. Yeah,
All right, sounds good.
excellent.
Well, a little bit about me. If you don't know me, I'm Raza Codes on the internet. I'm a DevRel. I love playing with tech. At Raza Codes where you can find me. So yeah, let's talk today about ZK rollups, EVM types, the holy grail of scaling solutions, as mentioned before by Vitalik. Quickly want to set the tone of what is a rollup. This crypto Twitter gets crazy about this, defining a rollup, but in simple terms, you have an off-chain network, not an L1, batches transactions, and then post these transactions on L1. Why? Because it solves the scalability problem that Ethereum has. The two biggest types of rollups that you find out there right now is optimistic and ZK rollups. We're going to talk about ZK rollups, but an L1 needs to prove, sorry, an L1 needs to prove that the transactions are valid. Two types of proof: validity proofs used in ZK rollups and fraud proofs in optimistic rollups. So in a ZK rollup, what is a validity proof? It's a zero knowledge proof that is submitted by the ZK rollup, and the proof is submitted on an L1 and verified on L1. Transactions are generated on the off-chain and L2 on the ZK rollup, and what the ZK rollup does is generates a proof that these transactions are valid. And so the way that the L1 knows the truth is that when the transactions are posted from L2 to L1, a proof is submitted alongside. So finality is reached.
So can I jump in here? Are you
Yes,
going to
sir.
go over the difference between validity proofs and fraud proofs?
No, I'm not.
Okay, cool. Can I ask that? Can I ask that right here? So for listeners who don't know, what is the difference between a validity proof, which is what a ZK rollup does, versus a fraud proof, which is what something like an optimistic rollup, like like an Arbitrum or an Optimism does? What's the difference there?
Yeah, so I guess I shouldn't have removed the slide, but in another
No,
presentation
you're
I did.
good.
But yeah, so I guess like in simple terms, when you look at an optimistic rollup, when the transactions are basically executed on an L2, what happens is when that L2 communicates or submits the transactions on L1, there is a period for an honest party, any trusted party, to come and challenge whether the transactions are valid or not. And so in that arbitrary period, 1 week is most common used, but really it's arbitrary, meaning it can be any period. A fraud proof can be submitted, where a fraud proof would be proof that a fraud has been committed or like a malicious transaction. A validity proof is the other way around. So when an L2 submits the transactions, you kind of get a receipt and saying, hey, this is the proof that these transactions are valid.
Awesome, love it. So just for people who are watching, the major difference there is these validity proofs enable you to kind of have this much quicker finality on the L1 because you're saying, hey, here's the proof that these transactions happen versus an optimistic rollup. They say, here's the transactions. And does anyone disagree that these are the transactions? No. We'll wait a week. Cool. Nobody disagreed. Great. These are finalized. So is that kind of the main difference there?
Yeah.
Awesome. Cool.
And then so why ZK rollups is actually maybe to like one sentence on that as well. is that maybe the listeners already kind of figured it out, but the whole idea would be is when the transactions are submitted by this L2, immediately immediately close to immediately, not immediately, but a proof is generated, and so we know, okay, cool, we don't have to go back and challenge these transactions or look for a malicious transaction. It has been done beforehand, sort of your checks and balances. Cool. So that's how L1 knows the truth. And then something I actually want to highlight for the audience as well is we'll dive into later. You see a graph. This was created by Vitalik to basically give context on the ZK rollup landscape. So if you're not familiar with type 1, 2, 3, 4 EVM, basically every ZK rollup is slightly different, being that, and they can be classified into types. And that has everything to do with how close a ZK rollup is to EVM, being that Ethereum L1, and or versus how fast does it take, what is the performance to generate a proof. Now, I like to simplify it, and if you look at this, basically what this picture shows you is if you're closer to Ethereum, it means that the L2 will allow you to use Solidity, will allow you to use Yule, Viper, basically everything that you know right now, the dev tooling you use right now, and you can utilize it on the ZK rollup. And that is also classified as EVM compatibility. So on a bytecode level, this ZK rollup acts and behaves the same as Ethereum. Whereas a type 4 uses under the hood a different virtual machine, and thus you have a compiler before it. And this is also known as a language compatible ZK rollup, and also classified as type 4. So just to give you a couple of examples, if you look today at Linea, Polygon, and Scroll, we're floating between the type 3, type 2, being that, you can use Hardhat, Truffle, Foundry, and develop everything that you have utilizing those dev tooling on these rollups. And then there is no compiler in between, but ZK Sync and Starkware, so Matter Labs and Starkware, they have what's called a language compatible ZK rollup, and so there is some translation to be done. Now, what is the trade-off? So I spoke about EVM compatibility. Well, it's performance. So what would be the design choice to be closer to, or not closer to EVM actually, being that you might face some incompatibility with today's tooling and language? Well, that's for the proof generation. So if I go back, if I go back, what you see here on two axes is compatibility versus performance. And so you can see my mouse, great. So what you see over here is that a type 4 generally is the fastest to prove, to generate a ZK proof. And we'll go into in a bit, like how long does it take to generate a ZK proof and etc. and why is it a problem? But closer to EVM, generally speaking, means it takes a longer time to generate a proof. Further away, faster.
So basically, if I can jump in here, so you're basically saying there are some trade-offs to maybe having an L2 that isn't exactly EVM, right? And the further away from the EVM you can actually get these performance increases. However, you lose some of this compatibility, which is why you have this access here. So let me ask this: so why is, you said Scroll, Polygon, ZK EVM, Linea, you said those are kind of flirting between type 2 and type 3, right? It's kind of this gradient. Obviously, the more you modify the EVM, the less compatible it is. Why are they flirting between type 2 and type 3? I guess we'll look at Scroll in specific. What are some of the major changes, if I can ask, that Scroll's made that make it kind of type 2, type 3?
Yeah, so as to why we would aim, let's say, a type 4 bytecode level instead of, let's say, language, that to answer that question, well, Scroll is actually very close to Ethereum Foundation. So it almost sort of spun out of the EF. And that comes indeed in a bit when I'm going to talk about Scroll, is where we're convinced about the Ethereum ecosystem and then the vision and mission of Ethereum. And so recognizing that, we want to, community is huge for us and we want to be close to that community and ecosystem, it's kind of like the evident, like it's the obvious choice to say, okay, hey, we want to be EVM compatible, and we stay close to that. As for Linea and Polygon, obviously I can't comment on that. Like, they probably have their own choices to be made there. I will say what you saw perhaps as well with ZK Sync is that Solidity is also recognized. That's why they introduced like the whole compiler and went that route. So generally speaking, the reason why we opt for a type 2 is because of that Ethereum aligned vision.
Right, which is great, right? But so let me ask what are some of why isn't it type 1? Like, what are some of the major differences between scroll and like pure EVM?
Yeah, so that becomes a very, I find it, to be very honest, I find it very a little bit of a difficult discussion, because type 1 almost for like a ZK rollup, I would say, would almost feel very difficult to achieve, because type 1 would indicate that on consensus level, the ZK EVM operates. Right now, type 1 is classified as Ethereum. So you're one-to-one equal to everything that Ethereum does. And we'll dive into the differences in a bit, like what does scroll support and what it does not support, which is only very little. And that's why I mean, like, we're moving towards type 2. But there are slight changes, some changes, some precompiles, for instance, that we don't support right now, because it's very difficult to generate a ZK proof for that. To be quite frank, I won't be able to answer like what anyone else is doing, because the space is moving very fast.
Yeah. Like, obviously, let's just focus on scroll here. But yeah, so like I don't know, like the precompile that always comes to mind is like what is it, EC recover.
Yeah.
Is it like, my first question would be like, hey, is that supported, or is that like not a precompile that works with scroll?
No, so I'm just gonna pull it up just to like I'll make sure I answer it.
No worries.
It correctly.
And I know we're kind of getting super nerdy here, so if we go too deep and you don't know the answer, that's cool too.
No, that's all good. I'm just pulling it up from my notes, but
that's the precompile that just always comes to mind, because I did like a hack analysis on one of the original Polygon contracts, where in one of the wrappers there was a check missing on the return value of that precompile, and it's just always, whenever someone says precompile, for some reason that's the first one that always comes to mind for me.
Yeah, my list is actually not showing up, but I will put it actually on my screen.
Nice.
So,
cool. Oh, this is great. So we're right in the docs here.
Yeah, we're gonna dive straight into the docs. But over here, what you can see is
can you zoom in a little bit here? And
sure.
And for people listening, for people listening and not watching, I'll try to summarize what we're seeing here. We're looking at the docs right now, and we're looking at precompiled contracts. And if you scroll up again, what do you see? What was scroll up a little bit? Oh, yeah. and different opcodes as well. So there's some opcode differences and some precompiled differences as well.
Yeah, so there are a couple of opcodes that are disabled. I think that those would be the most interesting to have a look at. So if you look at base fee and self-destruct, so if you would basically utilize, or if this in our EVM would be ZK EVM would be encountered, the transaction will be reverted.
So why, I guess my question here is, why are these? We don't have to go into each one, but why would you make the decision to disable some of these opcodes? I mean, for me, seeing self-destruct disabled is kind of like, oh, well, yeah, great. Like, I understand why that one's disabled. There's the original idea of like the EVM was like, oh, cool. Like, whenever contracts are done, we'll clean up after ourselves and call this self-destruct thing. And then, years later, nobody's doing that. We've in CodeHawks, we've done a bunch of competitive audits, and we've seen a bunch of people say, hey, like, you should add the self-destruct function to this protocol so that when it's done, you can like clean it up. Nobody's going to do that. Maybe sometime in the future there will be some rent paid, but in any case, I understand why you did that. But yeah, why some of these differences here?
Yeah, so I think the simplest answer is, and we can go as deep as you want, but the simple answer is that
it's a high level.
Yeah, when you look at ZK EVM, what the ZK EVM is doing is it's proving that every behavior that would occur in EVM, it's valid and occurs exactly as it would be in EVM. So I've got a slide for this. Is basically the process of basically proving every single of these steps it's extremely intensive, and it's why one of the reasons why up until a couple of years ago it just wasn't possible, or the overhead was enormous. So what happens is the ZK EVM in our architecture, we'll dive it in a bit, takes the execution trace from the sequencer and enriched information, and basically every opcode and the specific sequence, it goes through that specific sequence, the steps of the execution of the opcodes, and then it has specific tables and circuits, and it all proves these opcodes that the execution is valid and the behavior is exactly the same as it would be on their EVM. And this generates an enormous overhead, but due to hardware acceleration, you must have heard of polynomial sequences, and so mathematical equations. We've been able to do this in let's say minutes instead of hours and hours of computation. However, there are opcodes still where I would say they're ZK unfriendly. So there's still work to be done in order for us to support this. And then that's also important that I think we have a sentence in our docs. But basically in future, the goal is to support these opcodes and the pre-compiled contracts, but not right now. So we will do that in future parts of our roadmap. Did that answer your question?
Yeah, no, this is actually great. This is exactly what I was looking for. So basically, creating these proofs is computationally expensive. So
yeah,
it makes a lot of sense to me. So to make it easier at the beginning, we just say, all right, screw it. We're just not going to have them. And moving forward, the plan is to add them on later. Can you actually scroll back up? So one in particular stands out to me. So difficulty / prev rando always returns 0. So does that mean that opcode is supported, but it just always returns 0?
Yeah, at the moment.
Okay. So that's actually really interesting to me because it's something that anybody who's doing security and a protocol is planning on deploying to scroll, if you see somebody doing block.prevrando or block.difficulty, which a lot of protocols do, even though, that's usually kind of bad if they're doing it. A lot of protocols are like, oh, cool, we'll use this as like a randomness seed,
Right.
which is, terrible for a lot of reasons. But if you are doing some type of security review and you see block.difficulty or block.prevrando, you go, which chains are you deploying to? Are you deploying to scroll? If you're deploying to scroll, it's super predictable because it's always going to be 0. So that's really good to know. That's really interesting. Cool. Thank you for that.
Yeah, and I just want to clarify, it is possible to get to create the block difficulty. We do have that information. So, but not to introduce another bad way of randomization. But yeah, this is just to clarify anyone who might be confused on that end.
Wait,
cool.
Wait. What do you mean? Like it doesn't return 0 or?
This one does return 0, but we do have in our block explorer. You'll see in a bit. So we do you can see the difficulty of for creating the block. So there we have block difficulty there specified.
Oh wait, you guys have block difficulty? So is there like a proof of work happening? Where does the difficulty come from?
That's a good. So, oh man, I put myself in a squeeze. Well,
and then for people who don't know, the reason that this difficulty opcode was changing to prev rando is because previously in proof of work, the difficulty was like how hard the work was to like find the answer. But now that we're I explained that horribly. In any case, since we moved to proof of stake, we changed it to prev rando, which is kind of like the previous random validator value that's going to be used, and we say, hey, like that's going to be that's the value that this opcode returns. But so what Raza is saying is, hey, we actually do have the ability to have this difficulty, and that's associated with proof of work. So I'm like, oh well, are you guys is scroll a proof of work chain? Like what's going on there?
Immediately clarified, no, we're not proof of work. So, not to have that confusion in the world. Let me start by saying we haven't designed we haven't designed a consensus mechanism yet. We know that's not the stage that we were at. Right now, if you look at the ZK rollups, they all run some sort of a consensus mechanism because you need that for distributed systems. And what we have right now is proof of authority that we utilize.
Got it. Makes sense. And that's just, what's the difficulty then? Where is that coming from?
Yeah, I can show that when we query, but right now the difficulty, we're running a centralized node, so I'm not sure like how much exactly that would tell you,
Sure.
and how much, yeah. of information we provide.
I mean, yeah, it's not super. So right now it's going to return 0. There is some difficulty thing, but it's kind of part of the bootstrapping of Scroll. Or Scroll mainnet isn't live yet, so
Yeah,
all good. Makes sense. Yep.
cool. Just gonna go back to my slide over here.
Cool, and thank you for that tangent. That was super helpful.
No worries, all good. Here for all the tangents. So, yeah, Scroll aiming to be type 2. So when you see ZK rollups, you know, you want to classify them either being bytecode equivalent, language equivalent, and then the trade-off is compatibility versus performance. So now diving into Scroll architecture. And if you look at the Scroll architecture, this is basically a high-level view, and we will go deeper into it in a bit. But in essence, what we have is an L2, which is the sequencing layer and proving layer together, and then Ethereum, the settlement layer. Now, the way you interact with a ZK rollup like Scroll is I'm going to start by saying you bridge your assets. So the native currency where gas is paid on ZK on Scroll is ETH. So you need to bridge ETH to execute transactions. I'm going to give you a quick rundown of like what each node does, and then after that we'll go through a quick rollup process, and then I promise we'll go into docs and code. So execution node, if I go back, that's this node over here. It's on the sequencing layer. What the execution node does is it's responsible for gathering the transactions. It's comparable to the EVM, so it generates the blocks, you know, your RPC URL. It connects to this node, and it delivers the input for the provers, which if that doesn't say much to you right now, it will make sense in a bit. It interacts with the bridge and collects the L1 message from the bridge. The rollup node over here, what it does is it batches the transactions. It commits the transaction data on L1. So over here in the rollup contract, 2 things are posted: the transaction data and the proofs. And the rollup node is responsible for both of those things. And then something important: the rollup node pushes chunks and batches to the pool of provers via the coordinator. What are chunks and batches? Blocks are formed into chunks, and chunks are formed into batches. And in a bit, I'll show on the Rollup Explorer exactly how that looks like. And then when we go up, you see over here the provers. And this is a pool of prover, which is actually decentralized, not permissionless yet, but it is decentralized, which is part of the answer why Scroll that I'll answer in a bit as well. But what the prover does is, so we have a pool of provers, different nodes. They each take a chunk, and per chunk a proof is generated. It's done parallelization occurs here. So the coordinator can assign to different provers different chunks. Proofs are generated, and then these proofs are aggregated, because remember, a rollup posts a batch of transactions, and per batch there is a validity proof. And why do we aggregate proofs? Is because if we would post a proof per chunk, it would cost a lot in terms of gas fees. So we aggregate this and post it back on L1. I'm going to pause. Patrick, any questions?
No, this is making sense to me. So very similar to some of the existing L2s that have mainnet right now, right? So bridge contract, maybe there's some function in there. I would like the nerd of me is like, I want to see what the contracts actually look like. There's some function in there, something like wrap or bridge or something where you take your ETH, it converts it to what are you calling it, like SETH, Scroll ETH, or whatever it is. And there's some node, I'm assuming it's the execution node, that's constantly reading this bridge contract. Yep. And you lock the ETH in that contract, and this bridge node reads, oh, Raza locked 10 ETH in the bridge contract. Let's unlock it on this L2. Yep. The execution node does that. You can now do your normal stuff on Scroll. You can do DeFi. You can send money. You can do everything like that. And you do all your transactions. Eventually, those will go, all those traces, all those transactions, they're going to go to this proving layer, which it looks like, oh, cool. Oh, all right, awesome. That's coming next. So
now you're doing my work. I'm letting you do my work.
I got you, Raza. That's what I'm here for.
I know you do.
So it goes to this proving layer. It does all the proving. It looks like it posts. It actually doesn't post to this execution node. It sends it to the rollup node, which
Yes.
is okay. That's really cool. So it sends it. So the proving process, the proving and the committing back to mainnet is almost like a separate thing.
Yeah. So and we're actually yeah, you're sharp. So there are actually 3 phases.
Okay.
But I'm gonna walk through this this overview first, and then we'll go through the phases. So what you see over here is I just want to quickly emphasize what you said. So there's a sync service. Indeed, we listen to the bridge. You know, it collects the so-called L1 messages, queues them up, and then the sequencer also obviously pulls it out from the mempool, generates the blocks.
Actually, can I jump in here? So the execution node is, so right now that I'm assuming that's going to be run by scroll, right? Or
Yes.
Okay, got it. Makes sense.
Yeah.
So the execution node run by scroll. Great, keep going.
Yeah. So and just to be clear, I mean, we're open about that. So if you look at the execution node, rollup and coordinator, these are centralized entities at the moment, and yeah, totally have a roadmap for decentralization, but we'll touch upon that.
It. Cool.
But yeah, so the execution node is you can see it as your traditional EVM. Your rollup node is responsible for your interactions with L1 when it comes to committing data, and also pushing. So we have a database where we can push the chunks and batches. We can so the coordinator can read from it efficiently and assign it to the pool of provers. And over here you can see basically high level we have like zk-AVM prover, and then the aggregated prover pushes it back to the coordinator.
What is that database structure? What kind of database is that?
A DB Lang on top of my head.
Got it. Okay, cool.
Yeah. Yeah, and then from the DB it goes back to the rollup node, and we post the proof. I actually have it over in the phases, so let's use that as a phase 1, 2, 3. Like what happens? So user submits transactions to L1 bridge or sequencer. So that happens over here in the execution node. So over here you can see it in practice, and we'll see that in a bit. Is just that's the goal of EVM compatible, just an RPC URL that you pass through your dev tool. It generates the blocks from the transactions in the mempool and the message queue. So in phase 2 is the rollup node monitors the blocks and fetches transactions, creates proposes chunks, which is multiple blocks in one piece, and then batches are multiple chunks in batch together, and then it writes to the DB, commits a transaction to L1. So in this phase 1 we call it pre-commit. In phase 2 it's commit. So we will commit the data on Ethereum, and then phase 3 is, and it happens all in parallel, where the coordinator basically fetches the chunks, sends it to the prover network, generates the proof, goes back, and the rollup nodes sends it to the rollup contract. And we'll actually go into Sepolia in a bit, and we'll see what the contract looks like. How the transactions. So the transactions are not compressed. They're obviously binary encoded, but we'll be able to take a look at that in a bit. So I'll try to finalize this quickly. So pre-committed is phase 1, where if you trust Scroll, the transactions are available in a couple of seconds actually. So we have a block time. We aim for a block time of 3 seconds. And the second phase is what we call committed. Is where the rollup node posts the data, the transaction, uncompressed on L1 on the rollup contract.
So when you say uncompressed, in my mind, I'm thinking, okay, all transaction data is being posted to the ETH L1, and then I go, oh well, why are you even running on an L2 if you're going to just dump all the transaction data back on the L1? Isn't that going to cost a ton of gas?
That's a sharp question, and that's true. So we are going to compress it. We are looking at how to do that more efficiently. But right now, we post it as is. And by the way, I want to point out that that's actually one of the differences. Like you asked me in the questions, like, hey, what are the differences between ZK AVMs? That's actually something for a developer also very, very important to know, that some ZK rollups only post state differences, for instance. So
this is the whole transaction trace tree that Scroll is posting.
Yeah.
And is that because I'm just going, okay, well, why am I even bridging to this L2 then? Because if you're posting all the transactions, isn't that going to cost similar amounts of gas than just doing it on the L1?
So Uh, I guess it doesn't. Like, there are a couple of things. First of all, if you look at throughput, scalability comes in various forms. It's both in gas prices and throughput. So you still get the throughput benefits on L2. The second of it is that, yes, it costs a lot of gas, but we will compress it. But the way we post it, and we'll see it actually in how much gas it costs, it doesn't outweigh the benefit of doing everything on the L2.
Interesting. So right now it's uncompressed. It's going to be compressed in the
Yeah,
future, but it's not like a state proof, or excuse me, a state diff. It's literally the compressed transaction list.
exactly.
Interesting. Okay.
And then so from committed we go to finalized, which is, so finalized means the validity proof has been generated and been posted, and that can take at least 10 minutes and sometimes longer depending on the network.
Interesting. So if there's like this 10-minute finalized duration for the proof to be generated, for to be posted, is there opportunity? So immediately I go, okay, like how do I attack this, right? The security mind in me goes, all right, what do I do to break this? Is there an opportunity there for some type of MEV to swap in, for some type of something malicious to happen? It sounds like so long as that validity proof comes through and is valid, you would just always wait for the validity proof before doing anything. Like if you're designing a protocol and you go, okay, cool, scroll posted their stuff. If you don't wait for the validity proof, you're basically just doing it wrong. Like you just have to wait for the validity proof, and then you're going to be safe as long as you wait for that proof. Is that right?
Well, yes. Well, no, not entirely. Let me maybe spin it different. So,
sure.
When the transaction is when the phase 2 is when it comes into a committed state, I don't want to say like, oh, there's a guarantee that the validity proof will follow, but there are a lot of checks and balances that we do in order for let's say, before we commit the data. Now, the real question is actually when you look at the ZK roll, when we go to mainnet, that's when we actually see the timings and the time arbitrage. Let's say if there's a period to do something about it. What some ZK rollups do is they actually lock up the funds. So there is an arbitrary period like optimistic rollups where, quote unquote, funds can't travel. While there are other ways, I know there are like other ways to still do it. But just want to point that out. As of now, I had a meeting this morning with the engineers. I actually asked this question as well, and we went through like all different scenarios. The simple way I can say it is that will be extremely difficult. Now, we are in a process of being audited, and most of it is audited, and it's going really well. But that would pose a serious problem. In this case, yeah, I can basically say that there are checks and balances, safeguards in place, that the data wouldn't be committed, and that's why it takes minutes. The data wouldn't be committed if there wasn't a chance of, if there's like even the slightest chance that the validity proof won't be generated, the data won't be committed.
I'm looking forward to that audit report, because the difference between very difficult and impossible are very large when it comes to a hacker, right?
Yeah, and so here's the thing. The reason why I won't say something like, so I just want to clarify, because we're on the record. I just want to clarify is that it was explained to me as being next to impossible.
Got it. Love that. And yeah, as we all know, as engineers, nothing is technically impossible. There's computationally infeasible. So it sounds like the idea is for the committed phase to have it be computationally infeasible for you to have to wait for that validity proof. So that is really interesting to me. I'm really curious to see what this audit report looks like, because the security mind in me goes, nah, you got to wait for that validity proof, and you got to wait a certain amount of confirmations. But yeah, really interested to see what that looks like. Although we're kind of getting super nuanced at the same time.
Yeah,
we're getting super nuanced here, but yeah, really interested to see how that goes.
Yeah, I know it's all good, and we can definitely like whether that's online or offline, we can dive deeper into it. But as of now, I would say that checks and balances and safeguards in place, and Yeah, well, when it's out, I'll let you know.
Do you know when? Yeah, do you know when the audit or the security review will be finished?
No. Well, to be quite frank, like I'll just quote Vitalik on this. Isn't that he posted this meme where about the ZK circuit that was designed and had 34,000 lines of code. It's our co-founder himself. He said, things are bug free only for so long, especially when you're dealing with such large code bases. So a part of it is almost ongoing, where you see the researchers in the space, Zcaros working really hard together, on going to the next level. And I will have to get back to you on that, on whether we're actually going to publish something or in what shape or form is going to come out.
Sure, makes sense. Cool. Yeah, this has been really exciting. All right, yeah, let's keep going.
Awesome. Okay, yeah, I forgot to update the slide, so that's really bad for me. But we actually went through the differences between Scroll and Ethereum, which is, I'm just going to go back to the doc, which is really this page when we went on a tangent. So we covered this a bit, but I think the most important when it comes to is the pre-compiled contracts, and I explained a little bit before already where the difficulty comes from, which is the ZK circuit and the generating the proof.
Yeah.
One thing I do want to emphasize is that we have it on our roadmap, and we will be as much Ethereum aligned. Being Ethereum aligned is basically the goal.
Love that.
Yeah, and that's why it also says currently. It's that's the emphasis.
Got it. So something that actually came up. So Vasily is watching this right now and leaving some notes. He asked a really good question that I'm kind of interested in as well. On your slides there, you were using two terms almost interchangeably, but kind of not. You were using chunks and batches. Mm-hmm. Are those the same? Are those different? Is there a difference there?
Yeah, there's a difference. So a chunk is made out of blocks.
Okay.
And a batch is made out of chunks. And so when
got it. Okay.
Yeah. And so whereas the nuances, the importance is that the unit of proving for generating a ZK proof is on chunk level, and the unit of the aggregated proof is on batch level.
Got it.
But I just want to emphasize that it doesn't mean that we do some high level proving. No, we prove every behavior of the EVM.
Got it.
So we have circuits, and let me just show you, because I think visual just makes it a lot better. So we have circuits that are specific for sets of opcodes or an opcode specific circuit. And what these circuits are designed to do is they have so-called constraints. Mm-hmm. And so let's say rules in place, and they check exactly, does this set of opcodes or execution steps behave exactly as EVM? If it does, it generates proof. If it doesn't, it doesn't generate proof.
Got it. Cool.
Okay, yeah. And so I think that was actually most of my slide, where I actually was gonna say, okay, let's deploy on Scroll, and also dive into the docs. But I guess at this stage, I would like to go through the Rollup Explorer actually.
Okay.
Because we spoke about, I guess here the whole idea of batches and chunks.
Can you zoom in a little bit here too?
Sure.
And for those of you who are just listening and not watching, sorry, you should also watch, because he's showing us some cool stuff.
So per Vasily, his comment, I'm just gonna go. I think this is fine. So over here, what we can see is a batch index. So this is a batch, and it's made out of 13 chunks and 72 blocks. And so if I go into these 13 chunks, so over here, this is a chunk, and I click on it, you can see this chunk has 7 blocks.
Got it.
And so then here, this is the block, and and inside the block we can dive deeper, and then we can go into the well, it's not indexed yet, so
yeah, all good. So I think I get it though. So the chunk is what the validity proof is done on. That's what you're saying. So a chunk of X number of blocks, boom, validity proof created, and then you batch together these proven chunks in a batch and push that to the rollup contract.
Yes, sir.
Got it. Very cool.
And so over here, let's see, like, so these are committed. It seems like. So over here, you can see them finalized. Well, these are 2 hours
Nice.
ago, but these are the different stages that
Yep.
the Rollup Explorer shows.
And so finalized means the validity proof is there. You can pull it. You can move your money based off of the. Okay, very cool.
Yeah, the validity proof has been committed, and so this is the sorry, this is the rollup contract. Just gonna refresh the screen. So this is Sepolia. We're obviously on testnet right now.
Yep.
So over here, you can see this one is still pending, is being probably being committed as we speak. So this is 5 seconds ago, and so here you can see a committed batch and then a finalized batch. Which finalized being that, like we just mentioned, the validity proof came in, and so over here you can see everything that we post. So
Right.
to show the original, this is like what it looks like uncompressed.
Got it.
And
right.
Yeah, this is the full view. So this is the rollup contract, and then this is the bridging contract. So over here you can see all the messages that are being posted. Just
Cool.
refresh this one. Yeah. So what I guess I'll do is I will now dive into deploying on Scroll.
Love it. Okay, cool. So for those of you watching, now is a great time, or for those of you watching, or listening, now's a great time to take a quick break. We just covered a lot of information, and we're about to switch context here to actually deploying something. So for those of you who are listening, you can listen to the sultry sound of Raza's voice clicking away and deploying to Scroll. For those of you watching, this is going to be really interesting because we're going to see how similar this is to something like Foundry, how similar this is to something like Ethereum, right? How much our current tooling actually works here. So if you're watching, hit that pause button, grab some Wheaties, grab a coffee or something, and then come on back. If you're listening, same thing, but you won't get to see the coolness happen, but I'm sure you can imagine it happening. So let's dive in. Raza, do you mind zooming in a whole lot so that people who are watching can see? Yes. Lovely. Okay, cool.
Awesome. So what I'm going to do is I'm just going to paste a simple contract, Ether wallet, and we're going to deploy this using Hardhat.
Okay.
So I'm just renaming the file, and then let me see, going to the scripts, just making sure that I have the right script here.
So you'd have to change the contract factory to Ether wallet instead of lock.
Yeah.
Oh, nice. You got it. Okay.
Yeah. And then something that I'll actually take a minute to dive in, which is the config file. So I'm just gonna I need to remove this one because we recently changed testnets. So apologies, I need to paste here the new URL.
All good.
But I can show it how it looks like on our docs, the developer docs. So if you go to the developer docs, developer quick start, over here we have.
Can you zoom in here a little bit too?
Sure.
One more. Lovely.
One more. Oh. So over here you can see all the details that you need as a developer to get started. The RPC URL, chain ID, everything you need. By the way, quick tip for listeners: I really like chain lists. So if you go to we're on there as well. So if you go there, scroll and then include testnet, you can see us over here. So if you connect your wallet and add it, then
zoom in a little bit here. I guess we're done with this page anyway. So
yeah,
all good.
So yeah, I'm just gonna copy this one. Go back to my code editor, paste it over here, and save it.
So that's for forking. Are we going to deploy to the chain, or are we just going to fork?
No, we're going to deploy. The reason why I actually pasted it is if we were going to go in testing, which probably, to be honest, we won't. But I just wanted to showcase the URL.
Cool.
And I still had the old one. But yeah, the way I personally like to deploy when I'm just deploying real quick is Travel Dashboard, because I don't have to pass private keys and whatever configuration I have, I can utilize. So what I'll do first is I'm gonna do clear. Can you see it well, by the way?
Yep, this is good.
So we'll compile the contract. Okay.
Oh, we just got to change the version in the right here in the hardhat.js config. So just change that 0810. Sorry, I'm backseat driving. Go to the hardhat.config and change the version.
17, yeah.
Yeah.
What would I do without you?
You're using hardhat. What's up with that?
Yo, I'm sorry. I know Foundry. So just to be clear, I won't be showing it today. Foundry does work, but I will be honest. Right now, verifying.
Whoa! I wasn't expecting Foundry or Hat. I was expecting some Python from you.
I know.
You know? What's well, you've gone to the JavaScript side, huh?
No. But I'm going to show you some Web3.py. No worries. I got you.
All right.
So what I'm just quickly going to show you, if you don't have Truffle installed, you can do npm install globally Truffle, and then I actually have to pull up my terminal because I need to run the Truffle dashboard. So I'm just going to do that over here. Run the Truffle dashboard before you actually deploy. So I'll just pull that up. So we are running at localhost.
You wanna minimize the terminal. So for those of you who are watching, he's running Truffle dashboard in a separate terminal, and this will be similar to if you just put the RPC directly into your hardhat config, your Founder config, your Brownie config, whatever. Zoom in a whole bunch. Awesome, lovely. Truffle dashboard. For those of you who don't know, I'll just kind of wait. Okay, that's fine. This is your testnet account, anyways.
Yeah, it's a test, right? Don't worry.
Quick, Vasily, just block out how many him putting his password in for his MetaMask.
I appreciate you.
I got you. Let's also, John, if you're editing this, just block that out, and all good. So for those of you who don't know, Truffle dashboard, it's a way to deploy your smart contracts without having your private keys in a .env. You basically hit deploy, it opens up the dashboard, and you can just deploy right from your MetaMask, so you never have to expose your private key. A much safer way to deploy than actually exporting your .env. So they're using this.
Yep. So I've got it running in one terminal. So I'm going to go back to my VS Code, clear over here, and then we're going to run the command, which is basically how I run network and then Truffle dashboard instead of passing an RPC URL. You can if you want,
Nice.
but then when I do this, back.
And there's nothing special about your deploy. Oh, cool. And it just pops up as a signature request. Great.
Yep.
Connected.
So
awesome.
And then confirm.
You can zoom out just a little bit on the dashboard.
Oops.
There you go. Yeah. Zoom in one more. Oh no, that's perfect. All right, so cool. MetaMask comes up. Oh, it looks like 2 came up. But all good. Yeah. Let's see it.
Confirm. I clicked confirm twice. So
okay, yeah. So we confirm once.
Yeah.
Great. Lovely. So we're deploying this. Let's see it on the Explorer if that works.
Yep. I'm gonna go to. So we recently moved to Etherscan, so super happy with that.
Nice.
But you might
zoom way in.
Yep.
Lovely. One more click. One more zoom in click. Yeah.
So just gonna make sure I grab the right. I think I grabbed my wallet address. I'm not sure if I grabbed the right transaction. Yeah, so I grabbed my wallet address.
All good.
Let me see. Well, it's fine actually. We can just go. So this one is 25 seconds ago.
Yep.
It's this one. So we created successfully deployed a smart contract on Sepolia, and over here you can see the transaction fees and the gas price that it took.
Nice.
Which, as you can see, woohoo, doesn't take that much. And 1-to-1 compared to Ethereum. So for most Solidity developers, they won't notice any difference. What I will do is go to the Rollup Explorer.
And then, so Vasily asked another question, who's off screen right now. Since this is an L2 for Sepolia, is there an official faucet for the L2 so that people can get Sepolia ETH, bridge to Scroll? Is that the current process for deploying to this Scroll testnet here?
Good question.
Nice.
So,
okay, cool. Can you zoom in just a little bit here?
Yep.
Lovely.
So there are multiple ways. It's a great question, Vasily. So, sorry, Vasily or Vasily?
Vasily.
Okay, Vasily.
I
Yeah.
should I shouldn't even say anything because my American accent is horrible. Um, but yeah, okay, let's go.
Two ways to get ETH on Scroll. One would be to bridge, and I need to switch to Ethereum Sepolia over here. So I'll switch, and then over here, what I can do is bridge funds from Ethereum Sepolia to Scroll. So when I do deposit funds, confirm transaction, and then it will send. While this is busy, what I'm going to do is go to our developer docs and showcase that we also have faucets available to
Nice.
claim directly. So I can imagine that
I believe you. We don't have to go to the faucet. I believe you.
Okay, cool.
Can we go back to your deploy.js script actually?
Yes, sir.
Yeah, so in the docs there's the Raza says there's a faucet. Awesome. So if we're looking at this deploy script, there's nothing different about EVM here. There's absolutely nothing different here, which is awesome. So my question is then, so can we go to etherwallet.sol and let's play with this? If we go to etherwallet.sol, in here, let's just add in the construct. Let's just add a variable underneath address payable public owner. Can we add a UINT 256 public sum number?
Okay, UINT 256.
Yep, public, and then just some number.
UINT 256. So
or just
let's say
variable or number.
My
number, my fave. Okay, nothing. Just and then semicolon.
All right.
And in the constructor, let's do my fave equals block dot difficulty underneath the owner.
All right. So my fave, and then
equals block dot difficulty. All right. And this compiles and everything, right?
Yeah.
What happens when we deploy this? I'm super curious. It'll just deploy fine, right?
Let's take a look.
Right. So it compiles fine, obviously. Let's see if it deploys. So again, the reason I'm playing with this is one of the opcodes that is pseudo supported. It works, but it returns 0 always.
Yes.
So it looks like it deployed fine. I'm willing to bet then if we pulled the my fave number once this actually deploys, it's just going to return 0. So that's really interesting to see. So for all of you security researchers out there, for all you developers out there, keep this in mind, right? If you do, this will work differently on Scroll than other EVM chains. This will work differently on Scroll than another EVM. Very cool. Just wanted to showcase that yes, you can deploy this, but yes, it's going to be different. Very cool.
Yeah. By the way, actually, I wanted to show you, if that's okay, real quick on the Rolex Explorer.
It's completely okay, Raza.
If I dive into, let's say, a chunk, and then a chunk, and then a block, then a block. Let's go. So over here, you can see the difficulty.
Nice. Okay, so interesting. So what happens when can you zoom way in? Zoom. Yeah. So why don't you roll over that? For miner used to calibrate block generation time, no constant POA based networks. So it's just always going to be 2 then.
Yeah.
Okay. So then it'll return 0 now. Maybe in the future it'll return 2. In any case, really interesting, right? These are some of the subtle differences for you devs to be aware of when you're building systems here. And although I will say, if you're using block to difficulty as a random seed, please reconsider. Just for any EVM chain, not just Scroll. So maybe it's good that Scroll just says, hey, it doesn't really work because it's not great to use anyways. So
yeah, and maybe this is a good time to show or talk about the prover network and the decentralization that I touched upon.
Can you zoom in a whole bunch here?
Yeah, sorry. Okay.
Lovely.
So actually, I should not show. I want to show the slide, or the roll up node. I'm sorry. Okay, I apologize. I kind of lost where.
All good. So I think on the prover stuff, I think I kind of get it. I don't know if we need to go into that unless let me know if I don't have it right here. So once we do this execution on the sequencing layer on the scroll layer, right? There are these nodes on the proving layer listening to all these transactions that go through, and they go, okay, cool, time for us to make the validity proof. And what's interesting is what you're saying is so the provers are, it's not permissionless, but it is decentralized. So
Yes.
so I guess the question would be, so who are these provers? How are they selected?
Yeah. So right now we have a prover network, and checked with engineering this morning. Roughly 1/3 is run by Scroll, and 2/3 are some of our partners.
Got it.
And just to touch upon, let's say, the question that you had and bridging into decentralization is you mentioned the differences, and also maybe a common question being asked, is the sequencer going to be decentralized? So first of all, it's not centralized right now. It's not decentralized right now, but that is definitely the goal. But I'd like to I'd like to think that we really talk the talk and walk the walk by making the prover network like decentralized from the get-go. And so what we're figuring out right now is how to make it also permissionless. And the way we want to do it is to make sure that we don't burden the community. And what do I mean with that? Is that right now the hardware requirements for a prover are really, really high. So we want to make sure that there
Can I
are.
ask what those are?
Yes. So with my latest check this morning, it was 500 gigabytes of RAM.
Ooh.
Yeah, a
Okay.
couple of GPUs,
Okay.
and and of course,
So
by the way,
I run a bunch of nodes. Yeah, that's definitely on the heavier side. Very interesting. Thank you for the context there.
yeah, and so we're definitely working on optimizations to be done on that end, but we wouldn't want to come back into like the proof of work days, right? Where you had all these rigs and people making a lot of money, and then everyone like out competing each other. So and by the way, the decentralization of the proving network and the sequencer, as I was told this morning, is very closely related. So hopefully this is like a good sign to people. When you think about, okay, hey, what are the distinguishing factors? It's like we take decentralization super serious, and we really want to make it happen as soon as possible, but never, pace and speed never at the cost of security, and making sure that we don't have availability and security like properly in order.
Yeah, makes a lot of sense. So one of my main questions that I'm always thinking is, okay, well, why would I deploy here? And I think based off this call, I think I kind of understand the pitch here. Let me know if this is right or if I'm talking crazy, Raza. So it sounds like number one, this is a type 2 ZK L2. So
So
it's
we're between type 3 and 2 right now, but we'll be type 2. Yeah.
Excuse
Yeah.
me. Okay. So going to be type 2, between type 2 and type 3, mainly EVM compatible. The idea is that it's much faster, it's much cheaper, and it's a ZK rollup where you get this quicker finality. There is a lot of emphasis on decentrality. Right now, there's a lot of, I call them centrality training wheels. It's basically how every project starts. That you basically have to have centrality training wheels. It's got some centrality training wheels. It's going to be decentralized. It's going to be more and more decentralized as time goes on. And the ethos, which I actually do think is important, the ethos is, hey, we want to be really tight with Ethereum. We want to be tight with the EVM, which I'm a big fan of. Is that right? Is there a piece that I missed here?
No, yeah, I think that something that I didn't emphasize enough is, open source. So, us being open source, being huge. But when I'm definitely not pointing fingers or talking shit at this point, but community is being thrown out a lot, and the way we really try to showcase is by really putting the efforts in decentralization, saying, hey, what does it mean for us to be part of the community? So we're really trying to talk the talk, walk the walk, and so community on multiple angles. We're going to come out with a lot more like cool stuff where we say, okay, hey, you can showcase that Scroll is a place for community first, dev first, And yes, EVM line. Yeah.
Cool. Well, this has been awesome. This gave me a wonderful overview of Scroll. I feel like I understand it much better now. Is there? Let me just look at my questions to see if there's any other questions I want to ask you. I think I feel like I get it. I feel like it looks intuitive, which I think is phenomenal. I don't have to update my tutorials a whole bunch for this, which is great. I can just be like, use the tools that you use. The only knowing those EVM opcodes, those precompile opcodes, or excuse me, those precompiled differences, it seems like it's super straightforward. Go to the docs, you can see them right there. We could even test it out. That contract that Raza deployed, we could just call the my fave number or whatever we called it and see, the difficulty is 0 or 2 or whatever it was. Really straightforward. This looks phenomenal to play on. I don't think I have any other questions. Raza, is there anything else that you want to show us, that you want to walk through? Anything else for the dev community to know about Scroll?
No, I think we covered a lot. Something that I didn't get to do, and I have to do it because it only takes 1 minute, which is I actually have a Python script I want to showcase.
Yeah. Okay. So for those of you listening, Raza on Twitter, his name is Raza Rython, big Python fan. And, that was actually one of the reasons we became friends, was we were like, yo, Python, what Python? Because I'm a huge Python buff myself. And so to see him using JavaScript, I was just a little surprised by, but yeah, seeing him do some Python as well, that feels more correct to me.
So just to showcase, and lots of Python love, but just to showcase that the whole idea, and I want to end on that note, is that indeed EVM compatibility, use your dev tools, the languages that you're familiar with today, is that, I like to use web3.py. I think it's a great library to quickly query data on chain. And here you can see the latest data that I've just created, like I'm just getting the latest block data using the web3.py library. And if I would go, it might not be indexed yet, but here you can see the gas used, but I didn't format it properly. But I'm looking for the block number, which over here I can see 89760. And so if I would go back to the rollup explorer, and I'm not sure if, so over here you can see 40 seconds ago it's this one, and you can see basically the same data. But if you like it in your terminal the way I like it, then you can use all your current dev tooling that you're familiar with, and it works out of the box.
Lovely. Cool. Well, Raza, we went through a lot. We learned a lot about Scroll here. This was great. Thank you so much for chatting with me here. Thank you so much for bringing Scroll to us and showing us Scroll and walking us through Scroll. And thank you, everybody, for watching.
Thanks for having me.
All right. Take care, all.